Is it visible?
Yes, sir.
So in the yesterday's class, we discussed about the composite wall problem. Am I correct, Ma?
Yes, sir.
Okay. And we also discussed about the composite cylinder problem. In case of the composite cylinder problem, what happens is we have taken the example of a steam pipe as well as we discussed about the convective heat transfer coefficient. Yeah, when we have a hot fluid inside a tube and a cold fluid outside, and you will be having three resistances. What are all the three resistances we will be having, Ma? What are all the three resistances we will be having? How many convective and how many conductive?
Two convective.
Two, two convective or conductive?
So two convective and one conductive.
Two convective and one conductive. Okay, so you have a convective heat transfer coefficient of the hot fluid inside and a convective coefficient of hot fluid outside, and you will be having the wall or the cylinder material, okay, which is having thermal conductivity. Okay, so one will be the convective resistance offered by the hot fluid to the wall. The other one is the conductive resistance offered by the thermal conductivity of the given material. Okay, it depends upon material to material. And finally, the outer one, the convective heat transfer coefficient of the cold fluid. Okay, so that's why air cooling is not encouraged in case of multi-cylinder engines. We know that, right? IC engines have got fins. We will be discussing in module 7 about fins also, different types of fins: rectangular fin, triangular fin, circumferential fin, etc. Okay, so the purpose of fins is it is used in electric motors as well as it is used in single cylinder engines. The purpose is to dissipate the heat which is generated inside the engine cylinder to the surrounding fluid. Okay, but what happens is in case of multi-cylinder engines, in case of cars, buses, why they don't use it? Any idea? Why they don't use it, Ma? Viswapriya, Viswapriyan,
Yes, sir.
yeah. Why we don't use air-cooled engines in case of cars and buses? Others, any others? All of you are there? Kaushik?
The engine is placed inside the vehicle, so it won't be exposed more to environment.
Yeah, see, the thing is, actually, the rate of cooling for that is lesser for air cooled engines. Okay, so for a small capacity engine, okay, we can go for air cooling. Okay, even in costly bikes, okay, some of the bikes are having water cooled engines only, not air cooled, because what happens is that air cooling will not be sufficient to dissipate the heat. Okay, the main reason is I already told you about the convective heat transfer coefficient. The convective heat transfer coefficient of air is very much lesser, or gases is very much lesser. See, this is what, see, finally, that's what I said. I can give you a problem you can solve, and you can get even 30 out of 30 in CAT exam. Okay, but the thing is, where, how, why? See, you can see here the maximum free convection heat transfer coefficient H value is 25, and the minimum for liquids is 50. It's almost two times when compared to that of gases. Okay, so the convective heat transfer coefficient value of liquid is much more higher when compared to gas. So that's why even in power plant engineering, you might have studied gas cooled reactors will also be there, nuclear reactors, where they will be using helium, inert gases they will be using. I think so. Am I correct? Hello?
Yes. Yes, sir.
But liquid sodium is the commonly used coolant. The main reason is liquid sodium is capable of absorbing more heat, and it will be in liquid state even at a temperature of around 400 Kelvin or 500 Kelvin. That's the advantage in going for liquid sodium. Okay, so liquid metals are even in internal flow in module 4 we will be solving problems. Sorry, no, module 5. Module 5 we will be solving problems with liquid metals also. Okay, so it's very important that you should know the properties, convective heat transfer coefficient properties, thermal conductivity properties of all these materials. Okay, it's very important. Okay, so here we have a hot fluid uh, inside a pipe, and you will be having the pipe material, and you will be having a cold fluid outside. Okay, so the hot fluid and pipe material and cold fluid. The hot and cold fluid accounts for convective heat resistances. Okay, due to their different convective heat transfer coefficient values H1 and H2 respectively, and similarly, then due to the thermal conductivity of the material, we will be having conductive resistance. Okay, so larger the thermal conductivity, the resistance will be lesser, right? Smaller the thermal conductivity, the resistance will be higher. The resistance to heat flow will be higher. Okay, am I correct or not? Because we use bakelite in pressure cookers. Okay, the bakelite material is an insulated or poor conductor. It offers more resistance to the heat transfer, so that our hands won't get hurt when we take the pressure cooker from the gas stove. Okay, after cooking, when we lift it, we don't feel it. Am I correct or not?
Yes,
am i,
sir.
am I correct?
Yes, sir.
And nowadays in all the pans we have that. Okay, we have that made of that is, the handles made of proper insulators. Okay, so that the heat will not be transferred to our hands when we handle the vessels. Okay, so that's what I said. Especially the concepts of heat transfer, especially in power plant engineering, especially in gas turbines, in aircrafts, and similarly even in case of spacecrafts. Okay, all those things, the concept of heat transfer is very important. Okay, so we know that the density, which is again one of the important parameter. That's why we discussed about thermal diffusivity. Thermal diffusivity plays a vital role, ma. That is, what is thermal diffusivity? Here I have told you. I think it is K by rho c. Am I correct? Alpha. Thermal diffusivity is given by alpha. That is nothing but K divided by rho into C, where K is nothing but the thermal conductivity, rho is nothing but the density, and Cp is nothing but the specific heat capacity. So that is defined as alpha. So the thermal diffusivity gives us an idea about the how faster the heat gets traveled or transferred. Okay, so thermal diffusivity is also one of the important property of a material when we start designing, especially in steam power play stations, in nuclear power stations. The thermal diffusivity of the material is also very important. We have to discuss about that also. That is also very important, ma. Okay, so uh, since I handled power plant engineering also in the last semesters, and I handle thermal engineering, internal combustion engines, I will be saying some practical examples. Okay, but try to refer the textbook, especially in Senjal and in Rajput. They have done so many problems. Okay, because within the 45 hours we are supposed to complete the syllabus. Okay, so we have time restriction. Okay, but please go through the examples, different examples which were given, different cases they have given for various heat transfer. Okay, try to go through it. Okay, it's very important that you should have more knowledge about heat transfer. See, especially the subjects fluid mechanics, thermodynamics, heat transfer, all these three subjects are very important, especially mechanical engineering point of view. Okay, because especially the day-to-day life applications, we find more applications based upon these three subjects. Okay, fluid mechanics, thermodynamics, as well as this heat transfer. Okay, and these are all some of the assumptions, and I have already told you how we will be getting the conductive resistance in the last class. Thermal conductive resistance, I have told you, natural log of R2 by R1 divided by 2 pi Lk. In the last class I discussed, right? Am I correct? Am I
Yes, sir.
correct or not? Okay. And suppose if you have a composite cylinder like this, which will be having 2 or 3 layers, okay, and inner fluid temperature may be T infinity 1, and outer fluid temperature may be T infinity 2, and you will be having 3 layers. The 3 layers will be having 3 different thermal conductivities. So then you will be having 3 conductive resistances depending upon the 3 layers, and 2 convective resistances depending upon the inner fluid and outer fluid. Okay, so in some cases you will be asked to find out what is the overall heat transfer coefficient, U, capital U. Okay, so capital U also I have already told you. Okay, in the very first class I have discussed about what is capital U. Capital U is nothing but 1 by sigma RT into A, or 1 by R total into A. So in some cases, if you are asked to find out what is the overall heat transfer coefficient, then you are expected to find that also. Okay, so don't think that, sir, in the class you have solved only problems finding Q and interface temperatures, heat transferred and interface temperatures only you have solved. Don't say like that. Okay, suppose if you are asked to find out the overall heat transfer coefficient, you should know that. Okay, students, is it okay?
Okay, sir.
Okay, ma.
Okay, sir.
Yeah. Which one? This is the problem I asked you to solve, right? The third one. Am I correct?
Yes, sir.
Yesterday. Okay, let us solve the
Sir,
first
can
problem.
I say the final answer which I got for the heat loss?
Actually, you can see it from the recordings, ma. Because see, what happens is if we have the answer, then the students will not be having the curiosity to solve it. Anyway,
No,
I'll be
not like that, sir. I just decided to solve it, and I just wanted to like. Okay, sir. Actually, we can solve
No,
this
no,
together.
it's up to you. If you want to save it in MS Teams
No, no.
also.
What I meant was, I mean, we can still solve the problem, but I just thought I would share my final answer before.
Yeah, you can, ma. It's not an issue.
Uh,
Have you
okay,
solved
sir.
it? Have you solved it?
Yes, sir. I got the heat loss to be around 133.57.
What about others? Any others tried it?
Sir, I got 47.42, sir.
Okay. Shall I do it now? Everyone?
Sure, sir.
Yes,
Shall I
sir.
do it?
Yes, sir.
Yes, sir.
Okay. Let me start it. See, sorry, kindly bear with me because my system is also slow, and especially there is small time lag, okay, between you and me. Is it visible now?
Yes, sir.
Okay, so this is the question. Find the heat loss of an insulator for an insulated pipe carrying a hot liquid to the surroundings per meter length. Okay, so the length is given as unit meter, 1 meter length. Okay, of the pipe, given the particular, given the following particulars. Inner dia of the pipe is 10 centimeter, wall thickness is 1 centimeter, and then thickness of insulation is 3 centimeter. Temperature of hot liquid is 85 degrees C, and thermal conductivity of the steel is say 58. Thermal conductivity of insulator is 0.2, and then convective heat transfer coefficient for inside and outside are 720, and atmospheric temperature is 15 degrees. So everything is given. Okay, so you are asked to find out interface temperatures and heat loss. Now let me solve it. All of you, please take along with take down the given data at least along with me. Okay, no need to take the question because already it's there, and even in the chat box I put the question. Anyway, the first assignment I will give you by next week, ma. When you have the cat one, ma?
12th, sir. February.
February 12th. So then what I will do is today is 18th. I will give you next week. I will give you the first assignment in composite wall cylinders and spheres. I will give you. Kindly bear with me because I am using a very soft pen and writing pad. Okay, so this is the thing, ma. Okay, now we have R1, R2, and R3. Am I correct, ma? R1, R2, R3. Okay. So inner dia of the pipe is 10 centimeter. So R1, which is equal to 10 by 2, that is 5 centimeter, 5 into 10 power minus 2 meter. Am I correct? Am I correct, ma?
Yes, sir.
Hello?
Yes,
Okay.
sir.
And wall thickness is 1 centimeter. So 10 plus 1, 11 centimeter. R2, which is equal to 10 plus 1 divided by 2 into
So
10.
won't it be 10 plus 2 because it'll be the diameter, right?
I'm a yeah, that's correct. 1 centimeter here, 1 centimeter here. Okay. Yeah, that's correct. 10 plus 2 divided by 2. That's correct, ma. Okay. When we talk about radius, it will become 6. I am correct. I am correct. 5 plus 1. Here it becomes 10 plus 2 divided by 2. So that is 6 into 10 power minus 2 meters. Thanks, ma. Thank you. So 6 into 10 power minus 2. Okay. And R3. What about the thickness of the insulating material? 3 centimeter. So 3 centimeter here, 3 centimeter here, and 3 centimeter here. So totally it becomes 12. 12 plus 3, 15, 18. 18 by 2 into 10 power minus 2. Am I correct? 9. 5,
Yes.
6, and 9. Okay. Am I correct, ma? 5 centimeter, 6 centimeter, and 9 centimeter. Is it fine? Radius is? Hello?
Yes, sir.
Yes.
Okay, ma. Now, let TA be the inner temperature and T be the outer fluid temperature. And TA is given as hot liquid is 85 degrees C and outer ambient temperature is 15 degrees C. So, TA 85 degrees C and T suffix B 15 degrees C. Okay. Now, when we talk about the resistances, we have convective resistance, 2 conductive resistances, and 1 convective resistance outside. So, we will be having TA. See, try to draw this, then only it will be easier for you to understand. T2, 1, 2, 3. You will be having 3 temperatures, right? T1, T2, T3, and finally TB. Am I correct, ma? Am I correct?
Yes, sir. Yes, sir.
So you will be having T3 and finally you will be having T suffix B. So T1, T2, T3 and T suffix B. Now this is 1 by HA into A1 inside. This is natural log of R2 by R1 divided by 2 pi K1 into L. And this resistance is natural log of R3 by R2 divided by 2 pi K2 into L. And this resistance is, see, the arrow mark should be the other way. This resistance is 1 by, am I correct, ma? HB into A2. Am I correct? Is it correct here?
Yes, sir.
Let me check it out. T1 minus T2 divided by natural log of R1 by R2. So R2, R1. And then T2 minus T3 divided by natural log of R3 by R2 divided by 2. Okay, fine. Very good. And what about the thermal conductivity values? 58 for steel and insulating material is 0.2. Okay. Now you have to substitute. You have to find out all the resistances. Now we know that the heat transferred, net heat transferred is TA minus TB divided by the sum of all the resistances. Is it okay, ma? Is it
Yes.
okay?
Yes, sir.
Okay, ma. Now, let me take the second page. First resistance. Let this resistance, the first one, or convective resistance, right? Or convective one. Oh, we don't know the temperatures, right? Am I correct? First, we have to find out Q, then only we have to find out the interface temperature. Am I correct?
Yes, sir.
Yes, sir.
Yes, sir. Q first.
Yeah. Okay. 1 by HA into A. 1 by HA. What is the convective heat transfer coefficient given in the problem? It is 720. 720. And what is the area, ma? 2 pi R1 into L. Am I correct? Pi dl. Is it right?
Yes, sir.
Yes, sir.
Yes, sir.
1 by 720 into 2 pi into radius R1 is 5 centimeter, right? 5 into 10 power minus 2, and assume the length as 1 meter. So how much it comes? Kelvin by watt? How much, ma? Hello? Please solve it faster. If you have calculator, if myself I have calculator, I might have done it now.
0.004.
0.004, ama?
44.
44. Unit is Kelvin by watt, ah? What is the
Yes.
thermal conductivity unit, ma? Sorry, conductive resistance unit. I had told you in the last class we did, right? It will be in Kelvin by watt, right?
K by W.
K by W. Okay. Okay. So units are important, ma. Please don't think that I will be giving you full marks when you don't write the units. Units are very, very important. If you don't write it, I won't give you full marks. 2 pi K1 into L, natural log of R2 by R1. So substitute it and get the answer. Natural log of 0.06 divided by 0.05 2 pi K1. What is the thermal conductivity of the first layer? Yeah. The first layer is 720. Am I correct? 720.
Sir, it'll be 58.
No.
It won't be 720, sir.
See, thermal conductivity, K value. That's correct. 58. 58. I'm sorry. 58 into 1. How much it is? Solve it faster. See, I have written here. What is the resistance? The natural log of R2 by R1 to 1 divided by 2 pi K1 into L.
0.00005.
0.0005,
Yes,
Yes,
sir.
sir.
Kelvin by watt. Okay, so this is the first conductivity resistance. The next one is R conductivity 2. So that is natural log of R3 by R2 divided by 2 pi K2L. So natural log of R3 0.09 divided by 0.06 divided by 2 pi into that value is very less. I think what it
Point
is?
two.
0.2. 0.2. 0.2 into 1. Yeah. How much it is? So calculate this one. Let me calculate the last one also. Or convective outer. In some textbooks, they used to mention it as R2. This is R1. And this is RA. R suffix A because of the inner fluid. And this is R suffix B. So whatever textbook you follow, you can do. Find out this. What is R conductivity 2?
I'm getting
Or
a
R2?
0.3228, sir.
Yes?
0.3228, sir.
0.3228 Kelvin by watt. Okay, unit. Or convective 2. That is again 1 by HB into A. So 1 by HB. What is the convective heat transfer coefficient? Outside it is lesser. 9. 9. Okay. So 1 by 9 into 2 pi R2 R3, the final radius.
9, sir.
Okay. So 9 centimeter, right?
Yes, sir. 0.09.
Into 1. How much more it is?
0.1965, sir.
196 Kelvin by watt. Okay.
Yes, sir.
Okay, ma. Now find out sigma R, ma. Sum of all these resistances. 0.196 plus 0.32 plus 0.005 plus 0.004. How much it comes? Sigma R 0.0044. So 0.0049 plus
0.5229, sir.
0.5229
5229.
Kelvin by watt. Am I correct, ma? Am I correct?
Yes.
Okay, ma. Now you can find out the heat transferred. Okay, since we have found out all the resistances, now finding out the interface temperature is also easier. The moment you find the heat transfer, automatically you can find out immediately the interface temperature. So it's very much easier. So now Q equal to TA minus TB divided by sigma R. So TA, what is temperature? Outside
85
temperature? 85 and
minus
15.
15.
Okay. So 85 minus 15 divided by the summation of all the resistances. Summation of all resistances, it comes to 0.5229. 0.5229. How much it comes, ma?
133.86, sir.
133 points.
133, amma.
133.56.
Heat transport.
130.54.
Okay, ma. How many of you got this answer? Those who tried? Nothing wrong in it. See, first time when you solve a problem, it's very difficult. As that's what I'm saying. I am handling this subject for the 7th or 8th time, so I can solve this. Okay, very first time if you solve, you will be doing small errors here and there. Okay, even I committed a mistake when I took the radius. Okay, so that's why you have to practice more number of problems. Okay, so now the second one is similarly Q, which is equal to TA minus T1 divided by 1 by HA into A. When you calculate, when we take the first resistance. When you take the first resistance, TA minus T1 divided by 1 by HA into A1. Okay, so we know that this answer. So which implies 133.5, which is equal to 85 minus T1 divided by 1 by HA into A1. Since we have calculated last, so we can easily take it from that. Some of the students, they don't do this individual resistances. Okay, so that's why again they will be repeating it. Okay, so it's a waste of time. Well, the moment you solve, you find out the individual resistances. Finally, finding out the interface temperature, it's easier. 0.0044. What is T1, ma?
$84.41, sir.
84.41 degrees C. Okay. Now, similarly, calculate the second temperature. Q equal to T1 minus T2 divided by natural log of R2 by R1 divided by 2 pi K1 into L. So we also know this value, which implies 133.5, which is equal to T1 84.41 minus T2 divided by the second value. Second value is 0. We have got something like that, 0005, 0.0005. How much it is? T2 will also be almost same. Am I correct?
84.34, sir.
84.34. Okay. So since the thermal conductivity of steel is higher, there is no difference between T1 and T2. Now find out T3. Q, which is equal to T2 minus T3 divided by natural log of R3 by R2 divided by 2 pi K2 into L. So which implies 133.5, which is equal to 84.34 minus T3 divided by what is that value we got? The resistance 0.328. How much it is, ma?
41.
How much? 41?
0.23, sir.
Okay, ma. See, you can take down this T2 minus T3 also. Sometimes if you want to solve, considering the last resistance. Okay. Since we know TB, T3 minus TB divided by 1 by HB into A2 also give you the same T3 value. Okay, don't worry. You can solve that in that manner also. You can solve. Okay, some of them they ask me, sir, why can't we solve like that? Yes, since you know what's that TB, you can take down the last circuit and you can solve like that also. Q, which is equal to T3 minus TB divided by 1 by HB into A. So again 133.5 which is equal to T3 minus 15 degrees C, I think, right? 15 degrees C divided by 1 HB into A is we have already found out that it is 0.196. Okay, so we can find out what is T3 like this also. Please cross verify it whether you are getting the same T3 value.
Yes, sir. Same.
Same, right?
Yes, sir.
So
Yes, sir.
41.23. Small minor decimal values may be different. Okay, depending upon some of them they will be taking 0.19. Some of them they will be taking 0.196. So small minute decimal value will be changed, but final answer will be how much it is? 40.
1.23.
Okay. So the same value. Okay. So don't worry. Whichever is easier for you, convenient for you, you can do. Okay. Okay, students. Okay, ma.
Yes, sir.
Okay. There is one concept of a critical radius of insulation. Let me explain it, and then I will come to this fourth problem. This fourth problem, it's often asked in GATE examinations also, ma. The reversing of insulation materials. It's very, very important. Okay, even in the GATE question papers, you will be seeing this. Okay, the fourth problem. Okay, because it involves a critical radius of insulation concept. Is it visible, ma?
Yes, sir.
Okay. Alright. Yeah. Now, see what happens is in the previous problem we solved one numerical where if we add insulating material, what happens is the thermal conductivity value reduces. Am I correct? Sorry, the temperature, surrounding temperature or the heat transfer to the outside reduces when we have the insulating material with lesser insulation value. Lesser thermal conductivity value. I'm sorry. If you have an insulator with a lesser thermal conductivity value, we have reduction in temperature. Do you see that the thermal conductivity of steel is higher? So the temperature T2 is almost nearer to T1, 84.4 and 84.3. Am I correct? Am I correct, ma? Hello? Hello?
Yes, sir.
Am I audible?
Yes, sir. Yes.
Yes, sir.
Okay, so in the last example we have seen T1 and T2, there is no change in value. The main reason being is, okay, the diameter is thin, and the other thing is it has got higher thermal conductivity. But if we have one insulator, then what happens is there is drop in temperature from 84 degrees to 41 degrees C due to the insulation material or due to the poor thermal conductivity of the insulator. I have already told you in the classes that insulator is a poor conductor, right? Insulator is a poor conductor. Okay, now what happens here is when we add insulation to cylinders and spheres, okay, so what happens is if we keep on adding the thermal resistance, it initially causes the thermal resistance to decrease, thereby increasing the heat transfer rate because the outside area for convection heat transfer is getting larger. At some critical thickness, the thermal resistance increases again and consequently the heat transfer is reduced. To find out an expression for critical radius, what happens here is, see, you can see here, this is T1, this is Ts, and this is T infinity. T infinity is nothing but the outside temperature, and T1 is nothing but the surface temperature, and Ts is nothing but T1 is the inner temperature. Okay, T1 is the inner temperature of the tube, and Ts is the surface temperature at the end of insulation, and T infinity is nothing but the surrounding fluid temperature. Now, what it says is, see, suppose if we increase the thickness, okay, what happens is the outside area for convection heat transfer is getting larger. Okay, so the area, we know that 1 by 2 pi R2H. Okay, so if the radius, if we keep on increasing the thickness of insulation, then 1 by R2H, this radius also, it also keeps on increasing, right? When it keeps on increasing, what happens is, again, there will be that is the heat transfer increases and it reaches a maximum limit, and then what happens is the heat transfer rate decreases or the thermal resistance increases again. That is the concept. Let me draw one diagram. Okay, so if we have this is the heat transferred, this is the radius. So if you keep on increasing the radius, what happens is the heat transfer increases, or in other words, the thermal resistance reduces. Okay, the heat transfer rate increases, it reaches a maximum peak, and then again it reduces. Okay, now what happens is this particular radius is said to be R suffix C or RCR, critical radius. Okay, RCR is nothing but critical radius of insulation. Okay. Now, why this heat transfer increases when we increase the radius, or thermal resistance reduces initially? Practically, it turns out that additional adding insulation in cylindrical and spherical exposed walls can initially cause the thermal resistance to decrease. When thermal resistance decreases, heat transfer increases. Why the thermal resistance decrease, ma? Any reason? Any reason? What is the reason? Am I audible?
Yes, sir.
Because the radius increases 1 by 2 pi r2, right? 1 by 2 pi r2. This r2 increases. Naturally, what happens? Naturally, what happens? 1 by 2 pi r2. So when this denominator value increases, this resistance, what will happen to the resistance value?
Decrease.
Decrease.
Okay. So, and again, here also, you have natural log of R2 by R1. Again, there is increase in value. Okay. So, what happens here is the thermal resistance reduce. Okay. And the heat transfer increases. That's why I have drawn this heat transfer curve. Okay. So, the heat transfer slowly it increases and it reaches a maximum value and then again it reduces. Okay. So, now when we want to provide insulation to steam pipe, okay, for steam pipe and all, we will be we have to give insulation greater than critical radius, RCR greater, okay, greater value. RCR should be higher. Okay, see, the radius of insulation should be greater than RCR. It should be greater than RCR. But for cables, electric cables, when we talk about electric cable, which one we should give? Which one we should give, ma? For electric cable?
Less than RCR, sir.
Less than RCR or equal to RCR?
Equal to RC.
Equal to RCR, that's correct. Okay, the heat has to be dissipated out. Okay, wa? Am I correct?
So if
Whatever
it's less
the
than RC, what would happen?
no, ma, less than RCR, what happens is that's what normally the electricians they used to have one insulating tape and they used to wind it, okay, the openings. But what happens is less than RCR also you can see here the heat transfer rate is lesser. Okay, it will lead to fusion of the material. See, since I have already told you, the bursting of cables takes place during summer. Okay, in all the transformers, we see sparkles arise out, and slowly what happens is the material gets fused, and immediately the electricians will be coming and they will be changing the cable. What is the main reason? The heat which is generated due to the high voltage which passes through, we know that, right? Even when we during night time, during summer, hot summer, we will be operating all the air conditioners, right, in our houses. Two air conditioners or three air conditioners which we use in our house, we will be operating it. Example, for example, multi-story buildings, we will be having 10 or 12 air conditioners, okay, and they will be operating it. At that time, what happens is due to a higher voltage passing through the cable, sometimes what happens is if the heat dissipation due to the heat transfer or due to the internal heat generation due to the passage of electricity through the cable, if it is not completely dissipated, then what happens is it will lead to bursting of the electric cables. That's why, as your friend said, when you have lesser RCR value, the fusion or bursting out takes place. Okay, so that's why critical radius of insulation is very, very important when we design electrical cables. Okay, when we design electrical cables, and to get the expression for this critical radius, we have this. We know that to find the critical radius, we know that that the overall thermal resistance when compared to when we calculate dRT divided by dr equal to 0, then what happens to this equation is dRt divided by dr, which is equal to 1 by 2 pi kr minus 1 by 2 pi r square h equal to 0, or r equal to k by h, which is equal to the critical radius. For cylinder, it is critical radius, which is equal to k by h. For sphere, it is 2k by h. Okay, so because the surface area, right? The surface area, depending upon the surface area formula, here you will be having 2 pi RL or pi DL, where I think the surface area is 4 pi R squared, I think. Am I correct? If my memory is correct, I think the surface area of sphere is 4
sir.
pi R squared. Am I correct?
Yes.
Yes, sir.
Yeah, so due to which RCR will be equal to 2k by h. Okay, so by considering the h value, right, by considering the convective heat transfer coefficient of the h value, usually the cables has to be prepared. Okay, but no one is following this in our I don't know whether these standards they follow. Of course they follow some standards, but I don't know whether it is up to the mark or not. Okay, so and that's what you can see here. For cylinder, if you have a k value as 0.03 and h value as 10, then the critical radius is 3 mm. But for sphere, it is for the same k and h values, it is twice, it is 6 mm. Okay, so yeah, now what I ask you people is, you try this problem. Okay, this is, as I mentioned earlier, okay, it's very important problem. You try this. Again, it is not with the critical radius of insulation. It's again a composite cylinder problem only, just like the problem number 3. Okay, let me paste it here, because I don't have the time, because when I try to solve it, it will take another 20 minutes. Shall I solve this now? Or
Yes,
can you try? Do you have any other work? Shall I solve this
yes,
one?
sir.
Everyone? Shall I
Yes,
solve
Sure,
sir.
this?
sir. We can solve.
Yeah.
Yes, sir.
Don't have
Yes,
any
sir.
other work, right? Because
No, sir.
some of them they asked me already, why can't we have it in the evening? That's why. Okay, let me
No, sir.
solve that problem there, and then we will wind up. Please, all of you, please tell me the answers uh, fastly, so that it will be easier for me. Okay, so
Okay, sir.
now a steel pipeline, what happens is, it is having thermal conductivity 50, inner dia is 100, outer dia is 110. It has to be covered with 2 layers of insulation, each having thickness of 50 mm. The K for first insulation is 0.06 and for second is 0.12. Calculate the heat loss per meter length of the pipe and interface temperature if the inside tube surface is 250 degrees and outside surface of insulation is 50. If the order of insulation is reversed, calculate the heat loss percentage. Okay, so now this is a slightly important. Why I say important? Because see, you are changing the layers of insulation. Okay, so first you have the pipe inner material, inner dia and outer dia. Okay, and then you have 2 radiuses of insulation. So there is no convective resistance, only there is conductive resistance only. Kindly bear with my diagrams. Okay, as I mentioned earlier, I am drawing it in a smooth surface. Okay, so this is R1, R2, R3, R4. Okay, so R1, R2, R3, R4. Now writing down R1, inner dia is 100 mm, so 50, 0.05 meters. Am I correct? 50 into 10 power minus 3, R1. Am I correct?
Yes,
Am I
sir.
correct?
Yes,
Outer
sir.
dia is 110 mm, so 0.055 meters, R2. Okay, it is covered with 2 layers of insulation having thickness 50 mm. So 50 this side and 50 mm this side. So totally 100 mm. 100 mm has to be added to 110. So 210 mm. 210 mm means then R3 will be 210, 0.105. Am I correct?
Yes, sir.
And similarly 50 mm this side, 50 mm this side. R4 will be 110 plus 200 mm. 110 plus 200, 310. 310 means 0.155. Am I correct, ma? The radiuses are correct or not?
Sir,
Hello?
correct, sir. Correct, sir.
Yes, sir. Correct, sir. Correct, sir.
Okay, ma. Now we have the thermal conductivity K1. We have three different values: K1, K2, and K3. So in the first case, okay, let me solve the first case so you can easily solve the second case and you can find out the loss in percentages. Okay, so what is the inner wall temperature? Inner wall temperature is 250 and outer surface is 50. So it is fixed. So this is fixed. So let it be T1. You don't know what is T2. You don't know what is T3, and outer is T4. T1 is fixed, T4 is fixed. T1 is 250 and T4 is 50. Okay, so the first you are having K1, K2 as 0.06 and K3 as 0.12. In the second case, what you are doing is you are having K2 as 0.12 and K3 as 0.06. Okay, that's what they say. All of you are able to understand the question?
Yes, sir.
So what happens here is natural log of R2 by R1 divided by 2 pi K1 into L plus natural log of R3 by R2 natural log of R3 by R2 divided by 2 pi K2 into L plus natural log of R4 by R3 2 pi K3 into L. Okay, so now the first case Q is equal to 250 minus 50 divided by R3 by R2 by R1. Please tell me the values more immediately. 0.55 divided by 0.05. Divided by 2 pi K1 into L. What is K1, ma? Assume unit length. Okay, assume unit length. Okay, length is not given. Length is given. Length is not given.
Yes, sir. Not given.
Okay, K1 is 50. 2 pi into 50 into 1. Similarly, substitute others also. Similarly, substitute others. Natural log of what is R3? R3 is 0.105. One not five by 55 or 0.105 divided by 0.00055. 2 pi into what is this value, ma? K2? K2 is 0.06, right? And K3 is 0.12. All of you are there?
Yes, sir. Yes.
Yes, sir.
Yes, sir.
And find out natural log of what is this 0.155? Yeah, 0.155 divided by 0.105. Okay, ma. Now find out Q. First find out this individually and this one individually and the last one.
80.6.
How much Q?
80.6.
18 point?
80, sir. 80.6.
80.4
4.
watts per meter. Am I correct? Hello? Is it correct, ma?
Verifying, sir.
Please check it faster.
What is the value? How we calculate that?
Am I audible?
Yes, sir.
Yeah,
Yes, sir,
calculated
yeah.
it. I think I have taken this problem from Sachdeva, I think. Hello? Found out the values, ma?
Yes, sir. Yes, sir. I'm getting around that.
Is it 80.4?
Yes, sir. I'm getting around. I'm getting 80.3. But yeah, we can keep it as 4.
Okay, okay, that's fine. Okay, ma. And now you have to solve the second case. You have to solve the second case and you have to get the result. Can you do it?
Yes, sir.
Yeah. Solve the second case. Only thing is the K value here changes. Okay, in the second case, what happens is here itself, let me change. In the second case, this becomes 0.12 and this becomes 0.06. Students, in the second case, the K2 and K3 interchanges. Okay, so K2 is that is 0.06 comes outer and 0.212 goes inner. Is it correct? Second case. Second case, this is the thing. What is the value in the second case? Please calculate. All of you are able to understand the problem? Only the insulator gets reversed. First case they use first material with K equal to 0.06 and second material is 0.12. In the second case, they use the 0.12 as the first insulation and 0.06 as the second insulation. Yes, what is the value you got? What is the value, ma? Second case? Hello? Are you there?
Yes, sir. Yes.
Have you taken down?
Yes, sir. Thank you.
In the second case, only K2 and K3 changes. for case 2. Yeah, what is the value? What is the value, ma? Hello?
Doing, sir,
Olivia?
doing.
Yeah. Why this much time? Because this value is the constant one. Only the second and third gets changed.
Yes, sir. Not to put in calculator.
Yeah, that's right. But you have to, you know, the first resistance. Only the second and third resistance changes.
Yes, sir. But still.
One not 5.82, sir.
First case you said 80.3. Even I don't have Sachdeva right in my house. I have to check. I had to go to college and I have to check there.
Coming on 105.82.
It increases, huh? That's correct. The heat transfer rate increases means it's correct only. I think so. How much it comes?
105.82, sir.
105.8. What about others? Charles, are you doing the problem? Are you there, Charles? Hello? Achudan?
Sir, I'm getting 105.76.
105.
Yes, sir.
Akhilesh, what is the answer you got? Anirudh,
Sir, I'm getting 105.76.
105.76.
Sir,
Okay.
104.
Okay, 104 or 105? Okay, ma. 105 watts. Okay. Now what happens is the previous cases it is 80, right? Why it is 80? Because now you can understand. Okay. So if you have the first insulator as a lesser insulator, that is value having a very less thermal conductivity value. Okay. Then you will be having heat dissipation less. Okay. So Q2 minus Q1 divided by which one will take percentage increase? Q2 minus Q1 divided by Q2 into 100. Okay, I think so. Am I correct?
Sir, in Q1, I'm getting 89, sir, not 80, sir.
Okay, Q1 you are getting 89 and
Yes, sir, not
Q2?
80. Q2 is 105, sir.
Q2 105, Q1 89.
Yes, sir, 89, sir.
What
Not
about
80,
others?
sir.
Somebody said 80.
Sir, yes, sir. Even I'm getting Q1 as 89.63, sir.
Okay, ma. Then it's not an issue. So 105 minus 89 divided by 105. How much it will be? Increase?
15.23, sir.
How much?
15.23.
15.23 percentage. Okay. So the increase is 15.23 percentage. Like this, you have to solve the problem. Okay. Now, what you will do is in the next class, okay, on Thursday, okay, I will not be solving all. Okay. Try to solve this fifth problem number 5. Okay. And all of you, please tell me the answer. I will not be solving this problem number 5. You have to tell me the answer. Okay. Okay, students.
Sir,
Yes,
which
sir.
problem? The fifth one?
Fifth one, ma.
Okay, sir.
Let me post it in the chat box. Okay. Let me post it in the chat box so that each and everyone will see it. solve the problem and okay, ma. All of you, can you solve the problem number 5?
Yes, sir.
Okay, ma. Okay, fine, ma. Thanks for attending. Thanks for attending. You can start leaving now.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Bye. Thanks for your patience. Bye.
Thank you, sir.
Thank you. You can leave, ma.
Thank you, sir.
Thank you.